Who is having the key? Okay. Bye. Thank you. Hello all. Welcome back.
Good evening, ma'am.
Good evening. Let us wait a couple of minutes more so that others can also join.
Okay, ma'am.
Yes. Okay, let us start the session. I'm sharing my screen now. Is my PPT visible? Can anyone confirm whether my PPT is visible or not?
Yes, ma'am.
Okay, thank you. So let us start today's session. Welcome back to the week 4 interaction session of course wastewater treatment and recycling. Uh, Yes, let us come back. So, those who are new today, let me give a brief introduction. I am Sethulekshmi. I'm a Prime Minister's Research Fellow and a third year PhD student in Environmental Science and Engineering Department, IIT Bombay. So, as a part of my PMRF teaching assistantship duty, I'm giving you all an interaction session like on a weekly basis for the course wastewater treatment and recycling. So this interaction session is intended to help you regarding your any doubts or about the content which is discussed in the course, as and also we will be discussing a few questions in this session which is prepared based on the previous year's assignment questions of this course. So this session will be helpful to you for solving the assignment questions and of the same of this course, and also it will be helpful for other the competitive exams, as the questions which we discuss here are also taken from the previous year's question papers of other competitive exams. So this is the purpose of this interaction session. So let us come back to the session. So first I am giving you a brief introduction on what you have learned on week 4. So I hope all of you have learned like all of you have gone through the NPTEL lecture videos. If not, kindly do it today itself. All the lecture videos are uploaded in the NPTEL course page. So kindly go through the lecture videos and then also attempt the assignment questions. I think that assignment is due for tomorrow. So let us have a brief introduction. So in the week 4, mainly you have learned about fate and transport of different contaminants which is released into the natural water bodies, say river. So you have learned about what are the various processes which affect the transport of different pollutants in the river, like the dispersion, advection, dilution, then like all those you have learned about all those transport parameters, and also other physical and physiochemical and biological processes which are happening when a pollutant is released into a river. So this fate and transport you have learned. Then you have learned about once when a pollutant is released into an upstream of a water body, what are the zones of pollution which is happening in the system, in the river system or in the aquatic system, and what are the methods by which the river or water body tries to self purify itself. So you have learned about different zones of pollution, and you have also learned in that you have learned about this a model with which we can predict the DO, the dissolved oxygen content in the river, which the model is known as Streeter-Phelps equation. You have also learned about the critical time and all, where the critical time is the time where in the river the DO is minimum, if it is if on this y-axis it is when it is DO, like dissolved oxygen in percentage, and T is time. You have learnt about how to calculate this TC, which is critical time where the DO is minimum, and what is the significance of this DO in the river, and all those parameters you have learned in week 4. And then after that you have learned about like this in the initial slides you have learned about what are the self purifying mechanism in the natural water bodies. But as discussed by the professor, always we cannot dump everything of anthropogenic nature into the natural water bodies. We need proper mechanism to treat the pollutant before disposal into the aquatic system. Otherwise, you all know what are the ill effects of pollution. So after that, the coming slides, you have learned about the engineered systems. We have various engineered systems which are designed to treat these pollutants to a level which is minimal, so that it won't alter the natural symphony or rhythm in the natural aquatic system. So the prime focus was on the engineered systems, and before learning the engineered treatment system, it is necessary to learn what are the various processes by which we can go for the design. So for that, for any design we need to have a grip on what is the mass balance for that pollutant happening inside the system. So you have learned about various mass balance approach which is used to know the flow of pollutant when it is reaching any system. So the next portion, the next slides were few slides were focused on developing mass balance equations or mass balance concepts in like I think in the NPTEL video we have discussed about 3 main type of reactors, which is CSTR, completely stirred mixed reactors, and then you have also learned about plug flow reactors and also batch reactors. So all these you have learned. The development of mass balance equations in these reactors are also focused on the lecture slides. So after that, a few problems were solved regarding the mass balance in reactors, and also regarding the self purification of river system or the aquatic bodies. So these are the things you would have learned
Excuse me, ma'am.
yes.
Ma'am, how many assignments were taken for internal mock, ma'am?
Okay, so that I will discuss with the concerned authority, and I will tell you in the next class. Is it fair?
Okay, ma'am. Thank you, ma'am. Thank you,
Yeah.
ma'am. Okay,
Thank you
ma'am.
for the question. It is noted. Yeah. Uh, so uh, so all these things were learnt in the week 4. So now I'll be discussing a few questions which is made with respect to the previous year assignment questions, and the solutions of those questions will also be discussed here. So let us move on to the questions. So first question is, which among the following is not a physical process in the pollutant degradation? Option A, advection. Option B, uptake of
Uptake of organic matter by microbes.
microbes. Option yes, I'll come back to the answer. Very good for the attempt. Option C, aeration. Option D, dispersion. So let us see the answer. Like any other lead. So one of you have suggested this answer. So any other answer? Anyone? Okay, let us see the answer. You are correct. Option B, uptake of organic matter by microbes, is the answer. The question here is which of the following is not a physical process. So advection is a method of transport of a pollutant when it is discharged into a water body. Like it is the physical process by which it is getting transported to other areas of the stream or system. So advection is a physical process. Then the third option is aeration. Aeration is also, it also comes under physical process, because in aeration, it is by the, like, from the atmosphere, the oxygen is getting transferred to the water body, and it reaches an equilibrium, and so it is also a physical process. Then dispersion, coming to the fourth option, dispersion, this is also a physical process, because it is also talking about the method of movement of the pollutant inside the system. So the answer is uptake of organic matter by microbes. It is a biological process. In the river system, in the natural system, many microbes will be present. As we have learned, the soluble organic matter will be consumed by these microbes. They will be getting transferred to the smaller molecules with various processes like hydrolysis and all, and based on that, the end product will be, organic matter will be converted to CO2 plus water. So so option B is the correct answer. So if there is no question, let us move on to the next question. Let us see the next question. So the next question is, the self-cleansing in rivers can normally reduce the pollutant levels of A. Microbes, B. Organic matters, C. Dissolved metals, D. All the above. So any lead on this? So this is a discussion forum, so you are always free to express your answers. So whether it is right or wrong, we are all learning together. So any lead, anyone? Self-cleansing in rivers can normally reduce the pollutant levels of. So if there is no lead, let us see the answer. Option B, organic matters, is the correct answer. So I'll tell you why. So self-cleansing in rivers can normally, like usually, like the microbes are always, first option is microbes. That is not the answer, because microbes are always present in the natural system. So like it is not that we cannot reduce the microbial concentration by self purification. Like even when you are discharging something into the river, microbes act on it. The BOD level will the BOD will reduce because of the action of microbes, and they will get converted to smaller end products, thus reducing the concentration of BOD, and in the end the pollutant concentration will get reduced, but the microbial concentration will still be there. So that is also one of the reason for which we are going for the engineered system, because in engineered system we have a control of like whatever is coming into the effluent. In the natural system, these limitations are there, because sometimes this organic matter will get reduced, but that also will be in the cost of other factors, like the, as you have learned in the septic zone and all, the fishes will get disappear because of the extreme low DO and all. So the microbes will be there. Then second is organic matter, which is the answer, because organic matter will get reduced eventually because of the self cleansing action of the river. And option C is dissolved metals. So dissolved metals will not be removed because they are inorganic in nature, and also in the later on stage of the week 4 presentation, you would have learned about the conservative pollutant and non-conservative pollutant. So metals comes under the category of conservative pollutants, because they are not biodegradable in nature. Therefore whatever concentration is there initially, that, like as it is inorganic in nature and also conservative, they will be there in the effluent or the downstream side of the river, so they will stay. So the fourth option is all the above, which is also wrong. So the correct answer is organic matters. So any doubt, anyone? doubt?
No, ma'am.
Yes, okay, good. So let us move on to the next question then. Third question is, which of the following statements is not true regarding zones of pollution in a river system? So first is, organic matter is decomposed in the septic zone. DO is near saturation in clean zone. Fish population is maximum in septic zone. Decomposition zone occur next to discharge point. So any guess, anyone?
C, I think.
C. Okay. Any other option, anyone?
Probably option D.
Option D. Okay. Okay, let us see the answer. So the correct answer is option C. The question is, which of the following statement is not true? So let us see the each option one by one. So first of all, let us see what are the different zones. Can anyone tell me what are the different zones when pollutant is discharged into the river?
Ma'am, first is the clear zone.
Good. Clear zone.
Then is the decomposition zone.
Decomposition zone. Yes.
Then septic zone.
Septic zone. Yes.
And recharge zone, I think.
Recovery zone.
Recovery zone, sorry.
Yeah. Good.
And then last second clear.
Clear
Clear
zone. Yes, very good. So these are the different zones. So let us see one by one. So when a pollutant is discharged into the aquatic natural aquatic system, like there are mainly these are the zones present. So prior to discharge, the river is not having any pollution, so it is known as clear zone. So once it is discharged into the river or the natural system, there starts the decomposition of the product. So in this zone, the DO level will start decreasing because of the decomposition action which started. So this zone is known as decomposition zone. So then comes the septic zone. In the septic zone, the DO level is so minimum that, like, you would have learned about DO deficit. The DO deficit is very high in the septic zone. In the septic zone, because of the extreme low concentration of DO, the many aquatic creatures like fishes would be absent in this zone. So then after that, like in this zone, like the pollutant would have got removed almost by 90 percentage. Example, 90 percentage removal would have happened by then. Like as the pollutant reaches the end of septic zone, it would have encountered almost a degradation of 90 percentage or 95 percentage. So then, like, there is not much removal is to be happened in the remaining zones. Only a little of the pollutant is left. Therefore the DO level will start increasing again because of the various action or natural factors like re-aeration and all. The DO will start increasing. So the next zone is called recovery zone, and at last the DO will reach a level which is near to the saturation level. So that zone again is known as clear zone. So these are the different zones. So let us see options one by one. Organic matter is decomposed in the septic zone, which is a correct statement because organic matter decomposition also takes place in the septic zone. So it starts in the decomposition zone, but it also continues in the septic zone, which is a correct statement. Option B is DO is near saturation in clean zone or the clear zone. Yes, that is also correct. And third one is fish population is maximum in septic zone, which is wrong because fish population will be a minimum or near to zero in the septic zone. The option D is decomposition zone occur next to discharge point, which is correct because next to discharge point the decomposition, once it is discharged, the decomposition starts because of the action of microbes and also in the presence of oxygen, and thus that zone is known as decomposition zone. So that is also a correct statement. So the question is this: which of this following statement is not true? Therefore the answer is option C. So any doubt, anyone?
No.
Okay, good. Let us move on to the next question then. So the next question is rate of reoxygenation depends on option A, temperature of water, option B, depth of receiving water, option C, flow of water body, option D, all the above. Any guess, anyone?
D.
D, all the above. Okay. Let's see the answer. Option D, all the above is correct. Very good. The reoxygenation means, like as I have said, you have the DO profile, DO in percentage. So like once a pollutant is released, the decomposition starts, and you know that DO will be consumed. DO, which is dissolved oxygen in the system, will be consumed for the oxidation of organic matter. So DO level will get reduced, and then like so this is the DO deficit curve. So again it will start increasing. So this increase is due to a process called reoxygenation. Reoxygenation means that the oxygen is getting supplied into the system. So there are various factors that affect the reoxygenation capacity of any natural body. So those factors are temperature of water. Like usually we say that when the temperature is low, DO level will be like maximum. So when the temperature is increased, usually the DO level is expected to be low. So I'm not going into the details of that. So the temperature of water is always a factor which affects the DO level in any natural body. Then depth of receiving water. Depth is also a factor because the reoxygenation takes place from the atmosphere. The atmospheric oxygen will get will get into the aquatic system. So like there are various laws governing that. The one of the classic law which defines is the Henry's law. We are not going to the details of that. So as the depth is more, as the depth increases, the bottom part of the river will be in the will get will be in the deficit of oxygen. So usually the surface of the water will have more transfer of oxygen taking place with the atmosphere, and thus depth is an important, depth of the receiving water is an important factor affecting reoxygenation. Then flow of water body. Flow of water body is also a factor because like sometimes like if the river is having very high turbulence, if it is having very high turbulence means there will be a good mix of water inside the system, and also there will be aeration happening from the atmosphere. If the flow is stagnant, then that water won't be having much oxygen, or like DO level would be less compared to the turbulent water. Thus flow of water body also affects the reoxygenation. Hence the answer is all the above. So if there is no doubt, let us move on to the next question. So let us see the next question. The question number 5 is most critical point in a river can be obtained by A. Setting up first derivative of the DO sag equation to 0. Option B. Integrating DO balance equation within boundaries from origin to critical. Option C. Equating the rate of deoxygenation to the rate of reoxygenation. Option D. All the above. So, any lead, anyone? Let us see the answer then, if there is no lead. So, option A, setting up first derivative of the DO sag equation to 0 is the correct answer. So, let us explain that. So, the most critical point in a river means, suppose this is DO in percentage, this is time, say in days. So as I have discussed earlier, initially the DO will be getting reduced and then it will start increasing. So say suppose this is the DO saturation. So this point is known as the critical point. Critical point is the point where the dissolved oxygen in the river is minimum. So this is the critical point. So as we have seen, this when the DO is minimum, it is also known as the septic zone. It happens in the zone called septic zone. So as you would have seen in the lecture videos, for calculating TC, which is critical time, you would have done like this first derivative of this say this DO. You would have like with Streeter-Phillips equation, we have the equation for dissolved oxygen. So when you take the first derivative of that and equating it to 0, like you would have got the critical time TC. So the question is most critical point in the river can be obtained by. So the critical we are asking about the critical time, the time taken to reach the critical point. So critical time is obtained by taking first derivative of this equation, the equation the expression for dissolved oxygen. So when you equate it to 0, you get the minimum value. So this is pure question is related to pure mathematics. You would have learned that in order to if you have a curve, in order to generate the maxima and minimum, basically you take the derivative at that point and equate it to 0, you get the minimum value. And if the curve is like that, to get the maximum value, the first derivative, when you equate to 0, you get this point, the topmost point. So this is based on that. So any doubt, anyone? So this question is from the derivative, the derivation you would have seen in the lecture videos regarding the calculation of TC, critical time. Any doubt? If not, let us move on to the next question. So next is a numerical problem. I want everyone to try this first, then we will discuss the solution. The question is a 20 mld untreated industrial effluent with 5-day BOD, 5-day BOD of 450 milligram per liter is discharged in a river having a discharge of 4 meter cube per second. So with background BOD, which is also 5-day BOD, is given of 1 milligram per liter. Assuming complete mixing, the 5-day BOD of the river water just downstream of the effluent discharge point is. So the question is given. So all of you please try this problem and then let us discuss the solution. So I'll give you about 3 minutes time. Similar question is discussed in the lecture video as well. So I hope all of you know how to solve this. So if not, anyway we will be discussing it. So please try this out. Anyone ready with the answer? Anyone? Anyone know the answer? Do you want more time or let us discuss the answer?
We can discuss the answer now.
Okay, sure. So let us see the answer. So this question, this problem is purely based on the mass balance. See, like you have a river. So you have an industry which is discharging wastewater into the river. So it is given that the industrial effluent is having the flow rate of 20 mld, which is 20 million liters per day, and the BOD is 450 milligram per liter. So the what you know about the river is that the flow rate in the river is 4 meter cube per second, and also BOD before discharge of this effluent into the river. BOD in the river is 1 milligram per liter. So what you have to find out is after discharge, soon after the discharge, what is the soon after the discharge, say let us say like if this is the discharge point, soon after the discharge, what is the BOD in the river? So this problem is purely a mass balance problem. Like you have a system which is a river, you have a mass of pollutants, and now we are discussing about concentration of BOD. Let us say it has a mass. So you know the mass initial, you know the mass which is coming, which is m naught. So what is the mass which is going out, final? So the mass flux final equal to whatever is there before plus whatever is coming. So this problem is a pure mass balance problem, which you have to do. The approach is this, like this is like weighted average we are taking, weighted average of BOD we are taking. So the BOD mix is calculated as QI, which is the initial, like QI is given 20 mld, that you need to convert it into meter cube per second, because the flow rate in river is given in meter cubes per second. So QI is 0.23, QI is 20 mld, which is 0.23 meter cube per second. 0.23 into BOD of the industrial effluent is 450 plus in the river the initial flow rate was 4 into BOD in the river was 1, which is given, divided by as we are taking the weighted average, the total flow rate after addition of the effluent will be this 4 plus 0.23, which is 4.23. So hence while evaluating this you get the answer 25.413 milligram per liter. It is just that you are mixing two things. You are mixing like A plus B and you are getting C. So what is the concentration of C? So as you are mixing, you need to do the weighted average approach. This is the weighted average approach. So any doubt, anyone? 25.413 milligram per liter is the correct answer. Any doubt? Okay. So this is one of the type of problem which will be coming in assignment, as well as like in some other objective exams and all. This type of problems are frequently asked. So the same type of problem was also discussed in the lecture video by the professor. So please go through that also and try to answer the assignment questions based on these basics. And if no doubt, let us see the next problem. Next is also a problem which is based on BOD. So I want everyone to try this out first and then we will discuss. So here two things are asked. Like I'll read out the question. A water sample is having a 3-day BOD of 120 milligram per liter. The rate constant is given, which is first order rate constant at 20 degrees Celsius is 0.22 per day. You have to find out the 5-day BOD and also the ultimate BOD. So two things are to be found out. So please try this out first. I'll give you about 4 minutes. Then we will discuss the solution. I'm telling you to try this out because like while you try only you will have doubts coming. So if you get doubts then you can discuss here. So that's why I'm telling you to initially try this out. So please try out this problem. What is the ultimate BOD which you are getting? Anyone?
250.
250. Okay, let us know. Very good. Any other answer, anyone? Uh, 5-day BOD have you got?
Now I'm calculating.
Okay. So 5-day BOD have you done? Anyone?
Ma'am, just 1 minute.
Yes, sure.
150.
Sorry.
150.
1
50. 150.
150.
Yeah.
Okay, let us see. I hope like any other answer, anyone? If not, let us see the answer. So yes, 250 ultimate BOD I am getting around 248. So your 250 is acceptable value. So it is correct. And BOD 5 I have got 165. So let us see the calculations now. So
Sure.
so first it is given that the 3-day BOD is given, which is 120 milligram per liter, and the rate constant, decay constant at 20 degrees Celsius is given 0.22 per day. So the equation is the, you know that like the BOD, which is the exerted or the oxygen equivalent to BOD, which is exerted, equal to at any time t equal to LT equal to L0 into 1 minus e raised to minus KT. The derivation I hope you have seen in the lecture video. If not, please go through the derivation of this equation. Anyway, you have to remember this equation. This is very important equation. At any time t, you get BOD LT equal to L0, which is ultimate BOD, into 1 minus e raised to minus KT, where K is the rate constant, first order rate constant of BOD decay, and T is the time at which you are calculating, like you want to know the BOD value. So this is an important equation. You have to remember this. So LT equal to L0 into 1 minus e raised to KT. Here 3-day BOD is given. So that means that LT is LT means L3. L3 is 120 equal to L0 is ultimate BOD, which we have to find out, into 1 minus e raised to K is given, which is 0.22, into time is given. Here we have the 3rd day BOD, so the time is 3 days, 3. So from this equation, when you calculate, you get L0 value as 248.37 milligram per liter, when you round off around 250 milligram per liter. So so this is how we have calculated the ultimate BOD L0. So any doubt, anyone? Any doubt?
No.
Okay, so let us see the second part of the question, which is calculate 5-day BOD. In order to calculate 5-day BOD, again this equation, L5 we have to calculate. L5 equal to L0 into 1 minus e raised to minus k into 5. Now we know what is L0, which is 250 or 248. 248.37, which I have got, into 1 minus e raised to minus 0.22 into 5. So the answer is coming as, when you evaluate this, 5-day BOD is around 165.69 milligram per liter. So you would have got 150 milligram per liter because you have used 250 milligram per liter here. So
Yeah, actually, there was some calculation around one. I have cross checked. It's 165.
okay, then fine. So this is the answer. So like this equation is very important. This type of question always comes in as assignment question, as well as for other this competitive exams. So this equation you have to remember. And also the another type which can come is, here they have given this k value and LT sometime, and you have been asked to find L naught, but sometimes you need to find out the k value. All other parameters will be given. So in these ways, this question can be changed and will be asked in the question. And sometimes that two LT values like uh, L3 and L5 will be given, L0 won't be given, and you have to find out the K. So in that case you need to find out the ratio of L3 by L5. It will be coming as 1 minus e raised to minus 3k by 1 minus e raised to minus 5k. You need to work out this equation and find out the k value. So in these ways this question can be modified and will be asked for the exams. So this equation and its derivation please learn thoroughly. Let us move on to next question. Next is a objective question. Which of the following is not true regarding completely stirred type reactors, CSTRs? So option A, content within the control volume remains in homogeneous state. Option B, stirring device is provided to ensure mixing. Option C, the concentration of a substance in outflow remains equal to that in the reactor. Option D, the reaction rates for contaminants in a CSTR are always zero. So any lead, anyone?
Ma'am, C.
Yes.
C is the answer.
C. Okay. Let us see the answer. The answer is option D. The reaction rates for contaminants in CSTR are always zero, which is a wrong statement. So let us see what is this continuous flow stirred reactors. I have drawn the figure. So these type of reactors are like, the assumption is that there will be like complete mixing. Whatever goes into the system is completely mixed in the reactor, so that the concentration and it reaches to like from C in, the concentration reaches CO because of the mixing as well as the reaction which is happening, the decay or generation, whatever it is, that process or reaction which is happening inside the system, the C in becomes C naught, and all the content, the entire content will get completely mixed. And when it is flowing out as the effluent, of course, like when there is only one exit and one entry, the Q will be same for both inflow and outflow. Like when there are many exits, then this is not applicable, but here in the figure, as there is only one entry and one exit point, Q is same as that of inflow. And regarding the concentration in the CSTR, the main speciality is the outflow concentration of the pollutant. C naught will be always equal to whatever concentration of pollutant is there inside the reactor. This is because of the assumption of complete mixing. So let us see options one by one. Content within the control volume remains in the homogeneous state, which is true because it is completely mixed in the completely mixed state, so that the content will be like in the homogeneous nature. Then option B, stirring device is provided, which is true. Stirring device is provided in order to ensure complete mixing. Then the option C is concentration of a substance in the outflow, which is C outflow, remains equal to that in the reactor, which is true. That is the main speciality of CSTR. Because of the complete mixing, C out is always equal to whatever concentration is there inside the reactor, which is also true. So the question, the option D is reaction rates for contaminants in CSTR are always zero, which is a wrong statement. Because see, let us write the mass balance equation. The mass balance is V into for any type of reactor, V into dC by dt equal to Q inflow into C inflow minus Q outflow into C outflow plus or minus V into dC by dt of reaction, whatever reaction is happening inside the reactor. So the option D is saying that this dC by dt reaction rates for contaminants in the CSTR are always 0, which is not true, because this is 0 only when the pollutant is conservative in nature. When the pollutant is conservative, it won't undergo any degradation inside the reactor. So in that case, this the reaction rate for this dC by dt is 0. But here we have nowhere it is mentioned that the pollutant is conservative. So this option D is the correct answer, because option D is the wrong statement. Any doubt, anyone? Any doubt?
No.
Okay, if not, let us move on to the last question of today's session. So this is a problem which is very important. So I want everyone to try this out first. Reactor is designed with a volume of 270 meter cube. A reactor is there. It has a volume of 270 meter cube. Then it is designed to treat a pollutant from to reduce the pollutant concentration from C in is given 90 milligram per liter, and the flow rate is also given. For the inflow, the flow rate is 250 kiloliters per day. 250 kiloliters is 240. 240 kiloliters means 240 into 10 raised to 3 liters, which is 240 meter cube per day. Then if the reactor, it is given that the reactor achieved steady state. You would have learned what is steady state in the lecture. If not, please go through it again. If the reactor achieved steady state, what is the outflow concentration? We need to find out the C out of the pollutant, provided rate constant is given. In the reactor, the rate constant is K is equal to 0.32 per hour, and CSTR condition. The reactor is operating in the CSTR mode. And so that is the first part of the question. The second part of this question has two parts. Second part of the question is, with the same outflow concentration, like C out, in the first part you get the C out value. With the same C out, you need to find out what should be the reactor volume when it is a plug flow reactor. See, suppose you know in the first part you know C in, C out, Q in, Q out. You need to work out what will be the volume of the reactor if you want to convert the CSTR into a plug flow reactor. So this is the question. So please try this out first, then let us discuss. Similar problems have been discussed in the lecture videos as well. So please try this out.
No.
Should we discuss or wait for your answer?
Ma'am, just 2 minutes.
Yes, sure.
We should discuss. Ma'am, you tell. Ma'am, you can explain.
Okay, sure. So let us discuss the answer. So let us come back. So first of all, when this type of problem comes, your first approach should be you have to write the mass balance equation, which is V into general equation V into dc by dt equal to q in c in minus q out c out plus or minus
No,
uh,
Papa.
all of you please mute yourself, plus or minus v into dc by dt. Here it is said that first order decay constant, so it is minus. So we have to write minus v into dc by dt of reaction. So the next approach is whatever terms can we exclude from this equation. So for that, first it is given that the reactor is in the steady state. So as you would be knowing, in the steady state there is no further change in the concentration when you take the system as a whole. Therefore, this v into dc by dt term, it will become 0. So that for steady state, the left hand side v dc by dt, which means that there is no change in the concentration when you consider system as a whole. So this in steady state it is 0. So the left hand side becomes 0. Then you know that there is nothing specified about multiple entry and exit points. There is only one entry and exit points. Therefore, q in will be eventually equal to q out. So which is equal to q in equal to q out equal to 240 kiloliters per day, which is meter cube per day. Then you know, so let us rearrange the terms. After rearranging, you get this q into c q out into c out uh, when you bring these terms to the left side, plus v into dc by dt of reaction. So it is said that first then you have to find out what is dc by dt of reaction. So it is said that it is first order. So usually the equation for dc by dt, or the rate of reaction, rate of change of concentration, is k into c raised to n. It is said that it is first order, therefore k into c. So it is k into c, which is as it is CSTR, c will be equal to c out. So I think I have explained it before, because in the CSTR, as the contents are entirely mixed, concentration inside the system will be what it is coming out. So this term will become v into this term will become v into k into c out. On the left side, so we have q out into c out plus v into k into c out equal to, on the right side you have this term q in into c in. Therefore, like when you take the c out common, c out into q out plus vk equal to q in into c in, implies c out is what you have to find out, q in c in by q naught plus vk. I have told you before that this Q in will be equal to Q out because we have only one entry and exit points. There is no place for this. Whatever flow is coming into the system, it will go out. So this term, when you substitute this Q in, when you substitute, it is 240 meter cube per day. It is given meter cube per day. C in is given in the question 90 milligram per liter. 9 milligram per liter. Then I have told you that Q out will be Q in. So Q out will be 240 meter cube per day, and volume is given 270. 270 into the 7.68 means K is given as 0.32 per hour. But when you consider this volume, it is given as this flow, we are equating it to the flow rate, which is meter cube per day. So here you have meter cube per day, here you have meter cube. So the K should be per day. So you have to convert this 0.32 per hour into K value with respect to day. So when you convert that 0.32 per 1 by 24 hours equal to 0.32 into 24, which is 7.68 per day. So that is what is used here. So when you calculate this, you get this value 9.33 milligram per liter. So 9.33 milligram per liter is the outflow concentration in this CSTR. Any doubt, anyone? Any doubt?
No.
I hope it is clear. If there is anything, you can ask.
It's clear, ma'am.
Okay. So in this type of problem, first you please write this mass balance, general mass balance equation. Then cancel out whichever terms which is possible. Like in this question, it is said that it is steady state. So the left hand side becomes 0. And then it is said that it is CSTR. So since it is CSTR, in the right hand side, C out will be equal to the concentration inside the system. Therefore, this C out will be equal to this, when you expand this, V into dC by dt will become, as it is a first order equation, dC by dt will become K into C. This C will be equal to C out. So K into V into K into C naught. So these terms you define properly. Then you whatever information is given as input, when you give it as input to the equation, you will get the answer. So this is the simplified approach. So let us move on to the next part. The next part, it is asked that suppose, like we know what is C in and what should be the C out. C in is 90 milligram per liter. This is C in. C in is 90 milligram per liter. C out is 9.33 milligram per liter. And we also know that when it is in the steady state, and suppose we want to build a plug flow reactor. Instead of CSTR, we want to build a plug flow reactor. So it is asked to find out the volume of the plug flow reactor. So in that also, same approach has to be done. First you have to write the mass balance equation. V into dC by dt equal to Q in C in minus Q out C out, minus, as it is dk, it is minus V into dC by dt of reaction. So from this, as it is a steady state, this will become 0. And in the plug flow system, see, this is the plug flow reactor. In the plug flow system, this Q will be equal. Q in and Q out will be equal. Q in equal Q out equal to Q. But C in, C out and C in the reactor, which is like in this 0 equal to, let us denote it as Q only, as Q into C in minus Q into C out minus V into, it is first order, K into C. The C in C naught and C are different because it is a plug flow system. Concentration in the uh, direction of flow of the system, it is changes at all sections. As you have learnt, there is no mixing in the this direction of flow. So the concentration will be different when you consider each section in the plug flow system. So in the lecture note, sir has derived the like based on this, the C in will be, if it is Cx, C out will be Cx plus delta x. So like that the derivation is given, and based on that this equation is formulated for plug flow reactor. C out, this is C out. C out equal to C in into e raised to minus kt. So this is developed from this principle. When you simplify this and by substituting these terms, C in as Cx and C out as Cx plus del dx, this derivation you can find out in the lecture notes. Please go through that. The final equation you get is this one. C out will be C in into e raised to minus kt. So from that you know you have to find out volume. So this will become C out equal to C in e raised to minus k. So time means time of flow, which can be written as V by Q. So am I right?
Yes, ma'am.
Yes. So we need to find out this volume. So now it is simple. We know C out, which is 9.33. C in we know 90 milligram per liter. K value we know, which is which is coming as 7.68.
7.6.
Yeah. Volume we don't know. Q also we know. Q is around 240 meter cube per day. Substituting all that and simplifying, we get the volume as 70.83 meter cube. This is the answer. So is it clear?
Yes, ma'am.
Okay. So for simplicity, you please remember this equation. C out equal to C in into e raised to minus kt. So if you can derive this from this basic equation, it is pretty good. But for emergency purposes and for easy solving, you can also remember this equation. For the plug flow reactor, this is applicable for plug flow conditions, plug flow reactor. So
Yes.
it is to be noted that in the plug flow system, the volume is less. Here it is only 70.83. For this much removal, for pollutant removal from 90 milligram per liter to 9.33, only this much volume is needed. Whereas in the CSTR, the volume was 270 meter cube. But both these systems, both plug flow and CSTR, they have their own limitations and advantages, which we are not going through right now. So this is all about this question. Any doubt, anyone?
No, ma'am.
Okay. So the next session will be on next Tuesday. Then there I will be discussing some questions related to this week 5 lectures. Same time. So if you have any query regarding this course, please mail in this mail ID. So this is all about today. So let us wind up this.
Sure, ma'am.
Any doubt?
No, ma'am. We can wind up.
Okay.
Thank you, ma'am.
Thank you. Thank you for your time.